Good morning, everyone. Can everybody hear me?
We can hear you, Lutz.
Yep.
Excellent, excellent. So good morning to my talk, Servo Interface Semantics, Tailor Expansions, and Inverse Kinematics Solving, and why you should care. I would like to start with, I mean, this is like super complicated words, and with the overall thing I would lead to. I've built custom cheap actuators myself because of the need of having cheap custom actuators. And this is the performance I get from my actuators, right? You see the target values at the top plot and the current value in the top plot. And at the bottom, you see the tracking error. This is the target minus the current value. And so I can send trajectories to my actuators, and they will follow this trajectory with at least an error below 0.5 degrees, right? This is like super decent tracking performance. But to get there, I had to kind of rethink the way I communicate my desired trajectory to the actuators. And this is what this talk is going to be about. So anyways, some words about me and the 01st RFC Berlin. It's a play on digital numbers, right? 01. We are going to found soonish, as soon as this Corona situation loosens up and we are allowed to form teams again. And most of us actually form a Humanoid veterans, and we just love robot football too much to stop doing it. If anyone happens to be in the greater Berlin area and likes football and is thinking about joining a new team in the Kid Size League, we would really appreciate you joining. Just head to 01.rfc-berlin.de and there you find a link to a Matrix channel where you could join. Right? This is where we organize ourselves. Anyways, as I said, we need cheap servos, right? We want to found a new robot football team, and the actuators themselves account for like 90% of the overall costs of robots. At least that was the case with the humanoids. And since we're not affiliated to any university or any company or whatsoever, we have to fund it ourselves. And paying 5K or 6K for a robot is just not feasible for us. So we need cheap servos, and cheap servos aren't readily available. So we kind of have to make them ourselves. And while at it, why not kind of reinvent them and make them as nice as we can? Right. So this is what I did. After my Corona project was building a robot dog, and there I did a design study, so to say, how we could do this. And I ended up having super cheap servos. They come at like 22 euros a piece. You've seen the tracking performance, and they theoretically could go to 4 Newton meters. I don't think they actually do, it's like 3, but I never measured it. And yeah. You see my cheat screen. Do you still see my cheat screen?
Not anymore.
Excellent.
Seems to be a thing about if you have the mouse on the left-hand side. Oh yeah, again.
That's tricky. Anyways, Servo Interface Semantics. This is the interesting thing. You know, with the old with the most dominant actuators we have in the Kid Size League, those are the dynamic servo motors, or right, like with a regular RC actuators, you always communicate the desired angle and how to get to that desired angle to the actuator. You're not really communicating the trajectory, and therefore the interface, how you communicate it, implies how the actuators work. And this also leads to how you formulate movement inside your control software. This is interesting. I just remove it then. Okay. So in a nutshell, old actuators work like, tell me where to go and how fast to go, and the actuators will comply happily. And this is, to me, this is kind of problematic, because at the end of the day, it always means the actuator lags behind the desired value, because I calculate the desired position for now, tell that to the actuator, and it will only move there if it's not there. If it is there, it won't move. Kind of makes sense, but I cannot really communicate, be now at this position and move ahead, right? And this basically means if you have a trajectory on the actuator where it has a change in velocity, right? It has to change from one speed to a speed in a different direction, then this overall scheme becomes very contradicting in itself, and you won't have the actuator move the way you want, not even remotely, right? So this is like a very basic example. Here I have a robotic arm with a piston joint and a revolute joint, and I want the robotic arm to move along a line. Yeah, it's laggy here too. But I just want to get the point across, right? So at the beginning of the movement, we have the prismatic joint being at value 0, and at the end, when the finger is to the rightmost position, it's at value 0 again. So if we would communicate this trajectory to the actuator at the very beginning, we would tell, hey, prismatic joint, please go to position 0, wherever you are at the moment, with velocity, say, -1. And it would happily comply by not moving at all, because it is already at position 0. And the next instant, it wouldn't have moved, and we would tell again, hey, dude, go to position 0 with a different velocity, and it just wouldn't move at all, right? So this is how it would look like. The prismatic joint not moving at all, but the revolute joint doing its movement, and this is not the trajectory in finger space that we wanted to achieve. So if you do have a robot at hand, try making that robot move a finger along a line. This is really, really complicated with the dynamics or any other actuators I know of, right? Unless you do hacks like look into tell the actuators a target value in the very near future, like a second or half a second in the near future. But this is a hack, right? This is not how we should communicate movement to the actuators. So this is why I changed the interface semantics. By that, again, I mean the way I communicate the desired trajectory to my actuators. Instead of telling where to go, I tell them a polynomial how to follow the trajectory, or how the trajectory should look like. I chose polynomials because they're very general, right? And I can generate polynomials for basically any function. And this is just a very general formulation of it. So I have a pi, which is the parameter of the ith component of my polynomial. Ti is time, t raised by I is time raised by I, and then that's basically it. And then I have to incorporate that into the PID controller of my actuators, right? Because I built them myself. This is what you know from Wikipedia, the ordinary PID formula, and this can actually be simplified and generalized to my scheme. Like if you have an n of your polynomial greater than 1, so you also incorporate acceleration terms, then you could also integrate that into your PID controller and get the bottom formula, and then it's not really a PID controller, more like you still have the I part, right? It's an I and then the remainder controller. I don't know how to call this properly. I like it, simplifies a lot, right? Anyways, back to the motion generation. Our servers now eat polynomials instead of values, and we do need to generate the polynomials, right? And since inverse kinematics is kind of my thing, this is why I spend lots of time on. This is it's kind of nice because I have an idea how to get there. But for you who don't know inverse kinematics, this is a bit math heavy. Please don't run away screaming. But in a nutshell, right, we have a thing which I refer to as task, which would be move the finger from the perspective of my torso along a line. This means I have a target function. This will be the line in torso coordinates. It's a function over t. And I have this is my theta, I have a psi, this is my value function. This is where is my finger with respect to q. Q is my posture. Posture means the value of each joint. Think of a vector, right? The first element of the vector is the value of the first joint. The second element of the vector is the second value of the joint, is the value of the second joint, and so on. But Q could also contain velocities and accelerations of your robot. Could contain everything, but those are like the state of the robot. Then I have an error function. This is how much I am off. This is what tasks are consisting of. Then I've written down this again. And then we go to the actual math. So the idea behind the derivation is we would like to minimize the error function over t, right? And we we are at a Q, we have a posture and would like to change the posture by a delta Q in order to minimize the error function that was introduced above. And we do so by having a loss term that weighs the error over delta Q with delta Q and the delta Q itself. Please don't pay too much attention to the C and W matrices. They are not important for this talk, but for a different thing. And we have a loss term. We want to minimize the loss term with respect to delta Q, yada, yada, yada. Then we do a simplification as an assumption, right? If we have the posture Q, we assume that our psi function, right, how our finger moves, is linear around our current posture with J, our Jacobian. This is the local, the partial derivative, the local partial derivative of our psi function with respect to Q by Q. And this is true, right? For small delta Qs, this is true. If I tweak a little joint, this means my finger moves in a certain direction very linearly, right? And with that, I can integrate that into a loss term. And this is the heavy lifting. The most important thing, I just have this here for the completeness sake, right? The most important thing is the equation at the very bottom, right? That one. This is how we calculate delta Q. Don't feel too scared. Let's assume for now W being identity, C being infinity, so it just drops out, and then we're left with a Moore-Penrose pseudo-inverse of the Jacobian. The Jacobian was introduced above, and if for inverse kinematics situations, the Jacobian is something specific to the task. That means if we move the finger from the perspective of our torso, the Jacobian can actually be quite easily calculated. It's just how we would traverse through the robotic arm, and then what if every joint would have an impact. The impact every joint would have on the position of the finger would be the column in this Jacobian matrix. Sounds super complicated. The math looks super complicated, but it's not that complicated to program. I know that because I did it. Right. So, point is, we can calculate delta Q, and we have a matrix, the Jacobian dagger. Dagger means pseudo-inverse, that can transform a coordinate in error space in our task space, that is the space where our finger lives in, to joint space, the configuration space. That's pretty neat. And we can apply this to form our trajectories, which we will send to the actuators, right? But first we do need to generate the polynomials. And this is where the Taylor expansion comes in case you don't know it, this is a quick recap. Think of having some function, which here is just a cosine shifted by something, and I just at 0.0, I expand the function by approaching it to a polynomial. With a polynomial, now we have a polynomial of rank 0, which is just a constant, right? So at position 0, the value 0, it gives just a constant. If I would apply a linear function, I have a tangent in that case. But if I have a function of rank 2, grade 2, like a square function, I have a pretty decent approximation around that value. This is what I do, right? Think about having a trajectory in task space, like this line, and I can transform this line thing into the space of the joints, and then do a local Taylor approximation. This is how I generate the polynomials I send to the actuators. In math, yes, 0 is the current value. Yeah, I just used 0 for this example because, I mean, over time it shifts, right? You could either have the time shift because time passes, or you can shift your trajectory to the left. It doesn't really matter, right? And then you just generate the tail expansion at the current whatever time point and send that to the actuators. This is the idea. This is what we want, right? We want to calculate a polynomial to send to the actuators. And this is how we integrate the tail expansion. You see pi equals 1 over factorial I, yada, yada, yada. This is how a tail expansion is calculated. So you set this into g of t, then you got it. And pick an n first, like an n to the upper bound of the polynomial degree. And with the inverse kinematics delta Q, it leads to this bunch of equations. The only important one is the bottommost, right? To calculate the eth part of the polynomial to send to the Jacobian, we need to apply this. This sounds or looks super horrible because I factored in the derivatives into the brackets, but I did this on purpose because psi of Q is really painful sometimes. If you happen to have a robot with revolute joint, and I'm pretty sure you do have, right? Psi of Q has to contain parts for Coriolis, depending on the point of reference, but at least for centripetal accelerations, right? So if your robot joint has a velocity, it means that the finger will accelerate towards the origin of the joint. And you have to do this for every joint, and then incorporate that into the derivative of psi of Q. But then you got it, right? And further derivatives of psi of Q are actually even more complicated. I never went beyond 2. I don't actually see any reason to go beyond 2, but you could, right? Anyways, this is pretty math heavy so far. I've implemented it all in my RoboControl software. Right? So position, velocity, yes, exactly. So position, velocity, and acceleration. So yeah, the trajectory, the polynomial ascent to my actuators consists of those 3 components. Position, the 0th component first and second, position, velocity, and acceleration. And the second derivative of my psi function accounts for that. The second derivative of my theta function accounts for that as well. I assume all my thetas to be derivable twice, at least. Okay, and this is why you should care. It looks like very heavy math and hard to calculate. It is not. Computers are very, very good at doing so. And you get insane tracking performance at the actuators. I don't have a comparison with the dynamics service which we had with the humanoids, the only ones I had at hand. But by concept, I couldn't achieve this tracking performance, to my knowledge at least. There's a notable exception. The Roban team has released a custom firmware for dynamics actuators, which kind of works similarly. They go to velocity, right? So they have a polynomial of rank 1, as far as if I understood it correctly, right? But this is very, very similar to what I did. And take a look at it. And we could get rid of the hack that every team I know has in their code to like over-exaggerate the target values to the actuators just to make them move a little bit more like we would like them to move. Because there was no other way. There's no other way to communicate our desires because the interface doesn't do well. Anyways, here's the tracking performance again. This is a plot you've seen before, and yeah, this is like the best possible case. And the trick is, I said earlier, we can reduce the frequency, how often we communicate or intent to the actuators. Therefore, we can free a lot of processing time. This is the performance at 10 Hertz. I go back to 500 Hertz and 10 Hertz. There is no difference, right? So this is crazily good. So I could just reduce the frequency of my motion planner a lot, free up a lot of processing time, and that's good. But it doesn't work arbitrarily well. This is at 5 Hertz, then the tracking error actually increases significantly, like by a factor of 2. And just thinking there was a question. There are 2 lines in the graph. Yes, there are 2 lines in the top graph. Sorry, I don't know if you can read it. There's 2 lines. There's a blue and an orange line. The blue line is the desired position, and the orange line is the actual position, the current position of the actuator. I sampled the current position at 500 Hertz, and I set at this experiment the target position at 5 Hertz. And the bottom graph is the current minus the target at maximum sampling rate. Right? I could do the same experiment with without sending acceleration values by just setting the acceleration values to 0. Oh wait, and no velocity. This is the closest thing I know how the dynamics of servos would behave. It is not the same. Please bear in mind, this is not the same. It's just, I kind of try to simulate the behavior of the dynamics of servos in my custom actuators. And the only important thing is, as you can see here, there's a shift in time. The actuators are not at the target position where I want them to be at the time when I communicate it, because they can't. This is not how this interface works. There's no chance for them to keep up with the desired values, right? And this is what you see here at best, at most, the best possible case with the highest update rate. And this is if we reduce the update rate, so the phase shift becomes bigger and the tracking error becomes bigger as well, because we are not really communicating the desired velocity and acceleration, and at a ridiculously low update rate. It's bogus, right? Ignore this plot better. Anyways, I do have a demo, right? Because I said earlier, I have a robot dog, and I created for fun. I gotta show you how this works. I hope you can see my robot and my stuff. So at the top right window, you should see the speed my software is running at, the frequency of my motion planning and everything. This is going at 100 Hertz. This is my robot, it moves. At the bottom, you see plots of current. On the left-hand side, you see the current values, the target values, current velocity, target velocity. My service is super noisy, and the velocity estimate of my service isn't that good. But anyways, for the sake of what I show, it works. Right? So I make it stand up. It stands up. Now I reduce the frequency while motion planner was working at to 20 Hertz. And it behaves exactly the same. It just freed up 80% of my processing time. Nice, right? This is the point I want to make. We could change the semantics, how we communicate to the actuators, and while doing so, get the cheaper actuators with an insane tracking performance and reduce processing time, right? And this is how I would like to end my talk. For questions, I would be delighted to hear you guys. I don't know if I quit the presentation entirely.
We still see you.
Are you guys still there?
We are still there, yes.
Oh no, it's like, shut down my speakers. Sorry. Are you guys still there? My bad.
Yes.
Okay, now I can hear you. How long can I go? You mean how long my robot can go?
How low? It was about going low.
20 Hertz, about that. This is why I didn't go any further. Seriously, if I go below 20 Hertz, it doesn't, you see a difference, right? So it stutters a little bit, because then the trajectories diverge too much between points in time when I update the trajectory on the actuators. I mean, this cannot go arbitrarily low, but I can safely reduce to 20 Hertz and to 30 Hertz with walking. It doesn't walk as nicely as with 100 Hertz, but like 30 Hertz, that works. Heinrich raised his hand. Can I unmute him or just call Heinrich, please?
No, I can unmute. Hi, hello Lutz. Good to be back.
thank you for the impressive presentation. And I have maybe just small remarks or like, question whether you see it the same way. So I see like several components in your approach. So one is of course regarding the lagging behind, no? But this is all about the prediction, right? So if I only always communicate the values that I want to have now, I will never get it, obviously, right? And I need an insanely reactive motor to achieve that. Yeah. So typically, like what we do, like we know, like with, I mean, we play with nows, right? So we don't have the luxury of changing our frequency rates and stuff. So typically what we do is that we know that our lag is 20 milliseconds, like 2 frames for us. And so we communicate the values that we want to have in the future. And the old interface, maybe I can post it, maybe somebody finds it interesting to look inside or so. What Aldebaran had, what we actually didn't use really, but what they had is that you could communicate several values in the future. And they would be interpolated some more linearly, right? So you could say like, oh, I think I would like to have those values, and then they're sent to the controller, and then somehow they're linearly interpolated. So it's much less sophisticated and stuff.
Well, you do have to pre-compute your movement then, right?
A little bit, yeah. But like, so you need to, so this is like a predictive control, right? So you predict how your motor will behave, like what would be the errors, right? And then you control it in the future.
Yeah, I think my stuff is like in between the two, right? I don't look too much into the future, but still try to be reactive, as reactive as possible. But I do look into the future.
Yeah, and so and the second component, like when one wants to just like unfold it, because there are like two maybe tricks or like two ideas that I see. The second idea is to move computation into the servo a little bit, right? So let's look at some of this. So
the servo has to know about the overall idea of the trajectory, or the trajectory at large, or about the robot structure. I don't know if this really is feasible.
Mm-hmm. So I like, because I didn't see what is exactly happening in this, like what is the servo doing with this polynomial? Is it doing something more than just sampling it?
Not really, no. So as soon as you communicate the trajectory to the actuator, it assumes t to be 0 and then just tracks time and applies this polynomial for every given point in time, and then has the PID controller running. So it extracts like target value, target velocity, and target acceleration every point in time, and then feeds that into the PID controller, gets a new control output, and applies it. That's it. It's like super simple code.
Okay, but then with a much higher rate, obviously, right?
Sorry?
But then with a much higher rate, obviously, right? So
well, of course, yeah. This sounds like I don't know, 20, 30K kilohertz. I don't know. As often as possible. So I do have 2 STM32s in my robot dog. Robot dog has 12 degrees of freedom, and each microcontroller controls 6 actuators simultaneously. They are connected via USB to my host computer, and it's pretty straightforward. There are some H bridges where between the actuators and like microcontrollers, and it's exactly how you would think to build it.
So, but like, yeah, no, that's great. And so, but then, so what I see is that if somebody wants, say, save the computational performance right now, and they have a bus of like 500 hertz, right? So they could split their motion right now with the dynamic accelerator in 2 parts. And the first part would calculate this polynomial. Of course, they cannot send this polynomial to the servos, but what they would do, they would kind of emulate the sampling that you have. The sampling is cheap, and then send it with 500 hertz, right? So this is like, I just wanted like mentally to separate these 2 features.
Yeah, you could. I would discourage you from doing that, but you could.
Why would you discourage?
It's still hacky, right? You still have the, you're not solving the problem. I would like to solve the problem, right? Anyways, but this is more a philosophical thing, and this is highly opinionated on mine. Don't get me wrong, dynamics and servos are fine. You get plenty of actuators, plenty of servo for your money, right? Those are fine actuators, but I'm more looking for a a solution where I do not need to touch it anymore.
Yeah, yeah.
By the way, maybe next year, I have an idea how to integrate this with comply and control, where you can have force control integrated into this as well. It would make the math explode a little bit though. But yeah, stay tuned for next year.
All right, thank you.
Thank you. Thank you. Is there anyone else?
Yep, me, but I have the green yes. So if that's okay for you.
Go ahead.
Okay, so just since you mentioned the Robin team, I can elaborate a little bit on that. So one of the problem we had was computing the trajectories for the future, because it was quite hard for people developing the motion to always think about the derivative, and we were up to cubic splines, I think. But one of the problem is, for example, when you're designing a kick motion, it doesn't go as well as when you have a sinus, because at some point you just want to use the maximal power from your servo motors. And there it's quite hard to guess the parameters which would allow you to get the maximal power with a quadratic or cubic spline. So that's something which made position control easier when you want to use the maximal power of your servo motors. And then I had a quick question. You say that what was interesting was also to get cheaper actuators. And how cheap are we talking about with what you're doing?
With my dog, I'm at 22.5 euros a piece.
Okay, and with what kind of torque and things like this?
I'm pretty confident I get 3 Newton meters out of them, but I've never measured. Like they are designed to go to 2 Newton meters. I cheated a bit, so I overdrive them with 12 volts instead of the supposed 6. But anyways, I've removed the internal electronics anyway, so they survive at 12 volts, even at stalling situations. They broke the plastic several times, the printed robot, and they're stronger than the plastic. I don't have any gear though to measure the strength. But yeah, I'm pretty confident they go to 3 Newton meters. And maximum velocity is, I think, 1.5 turn a second.
Okay, thanks a lot.
Yeah, if anyone has some gear in Berlin or whatever, just I would be delighted. I tried once with a super weird setup with a scale and just pushing on it, and well, I broke my setup while doing that. I'm not affiliated to any university anymore, so everything I do at home, and this is just toy tools I have basically.